In this video, I'm going to explain how R's probability calculations work and how you can use them for your homework or for anything for that matter. So you start out with a picture like this. So what we have here is the standard normal probability density function, or PDF. So that's what this purple curve is, PDF for a normal distribution. Bell-shaped curve centered at mu. So with these probability calculations, you're typically asking questions like the following. So you have some So say that x is distributed as normal mu sigma squared. Then you do statements like the following. The probability that x is less than some number q is equal to p. So these are the kinds of calculations you can do. So you can ask two questions of this, like this. You can say, given q, find p. So probability that x is less than q is equal to p. So this is the CDF, the cumulative distribution function. So it looks like, if I were to draw it, it looks like this. You draw a point Q on here, draw a line up through here. If I highlight this area over here, then the area here should be equal to, that I've highlighted should be equal to P. That's the area from negative infinity all the way up to Q. The area should be equal to P. So given Q, find P. In R, you do this as, here's an example. Suppose that you know the mean is equal to 10. Sigma is equal to 2. Then if you want to find the probability that x is less than 9, say. So here 9 is taking the place of q. So in R that would be p norm 9, mean equals 10, SD equals 2. Plug this in, it's approximately 0.31. I don't need all that precision. Okay, the other question you asked, given P, find Q. So what is the point at which, for example, 10% of the data is less than that point? Okay, so we want to find, for example, you take P equals 0.1. So these are probabilities, so they must be between 0 and 1 inclusive. So if we take P equals 0.1, then the R code is, write this down, R, Q norm 0.1, mean equals 10, SD equals 2. So here's an example of using this technique to get a 98% confidence interval for the mean. So this is simpler than doing the z-score method that your book recommends, but it's of course equivalent. It's exactly the same. It's just a little bit faster and easier. So suppose we need some numbers, x bar equals, say 6, okay, sample standard deviation is equal to 3.2. N is equal to 47, okay, I'm just pulling numbers out of here. So a confidence interval by the central limit theorem says that x bar is distributed as normal mu with sigma squared over n as the parameter. Okay, so then we can get a confidence interval. So we have 98%. So here's how we do our confidence interval. You take the quantile Q norm of, here we have alpha equals the 0.02, which is 98 divided by, so this was equal to 100 minus 98 divided by 100. So we take Q norm of alpha over 2, which are alpha over 2, so that would be 0.01. Mean equals 6. SD equals square root of standard deviation. You're plugging in exactly this formula, so you can take the square root of, let's just take the square root of 3.2 squared. You could do it other ways too, and then divided by n. Okay, so you can type exactly this into R and you should get the answer. So that's your left hand side. Here's your left, here's your right. It's almost the same thing. All the parameters of the distribution are the same. So it's almost the same thing. All the parameters of the distribution are the same. The difference is, instead of 0.01, it'll be 0.99 here. And that'll be your right-hand side. You plug these two numbers in. So you plug these two numbers in, and you get the following: to 16 digits of precision, 4.91, 7.09. So this is your confidence interval, just rounding them down. And that's how you do it. So you can do this rather than converting everything to z-score and using those multipliers. This requires fewer steps, and it's conceptually gets you to where you need to be of thinking of the distribution of the sample mean through the central limit theorem, which is the core of why all this works.